So in this video we're going to look at the math behind the ice cream lab and the idea of colligative properties in terms of boiling point elevation and freezing point depression or lowering. So the general idea was that if you have a higher concentration of a solution, more stuff dissolved in solvent, then you have more of a colligative property evident. So in terms of boiling point elevation, the more stuff you put in, the more energy it will take to get the stuff to boil, so a higher boiling point, thus boiling point elevation. So in your homework, you're going to see some examples of questions that will ask you a couple different things. Maybe how much the temperature is raised, or the new boiling point, or how much it might take to get a new boiling point, or a temperature raise to a certain degree value. So there's a couple things I want to point out in this formula. This is one of the formulas on the I can statement. So if we look at this, this right here, you might want to label this. Delta is change, and temperature. So this is change in temperature of the boiling point. It's a lot there, but that's what it is. So that the T is temperature and B means boiling point. So this is a change in temperature of the boiling point. So if the boiling point of water is 100, I make some salt water, it goes up to 105. The change total would be 5 degrees Celsius. So that would be delta TB in that example. KB, anytime you see a K, is a constant. And that constant, if you look to your right here, depends on what the solvent is. Each solvent has its own constant. It's you can think of it as a number that makes this change in the temperature of the boiling point, the difference, equal out with the molality or the concentration. So the concentration times the solvent's constant, or boiling point constant is what this would be called. So we call this a boiling point constant. Will make you aware of the change in the temperature of the boiling point. And again, this right here is molality. That's molality. Looking at a question, you're going to have some different variety questions out there, but overall it's going to deal with this. And realize that molality, we know the formula for molality. So you're going to be dealing with this equation, and at the same time, if you don't like to combine equations, realizing that molality is moles of solute per kilograms of solvent. And you could, in fact, make this one big formula if that makes sense to you, but you don't have to. Again, realize the change in the temperature of the boiling point is equal to the boiling point elevation constant, which is that KB right there, times the molality. So this is the word version of what the formula above says, but this is the formula we'll be sticking with for the most part. Again, if you want to combine this and make a giant formula to incorporate molality and this idea, delta TB equals K times moles of solute over kilograms of solvent. So if you want to, you can use that together. If not, that's fine too. So this question says, what's the mass of NaCl needed to dissolve in 1,000 grams of water if you want to raise the boiling point by 2 degrees Celsius? So some things you can directly plug in already, some things you can't. So let's look at, of the two equations up here, what I could potentially plug in. So these two equations right here. It says what mass of NaCl, so I'm looking for grams of NaCl in the long run here. I have 1,000 grams of water. That is going to be eventually my solvent right there, so it's solvent. And the 2 degrees is my change in the temperature of the boiling point. I want the boiling point of this substance to go up 2 degrees. So the boiling point I'm shooting for here, just to differentiate between change in temperature of boiling point and boiling point, the new boiling point, realizing that water, it boils at 100 degrees, the new boiling point would be 102 degrees Celsius. Alright, so I'm going to plug in what I know and solve for what I don't know. I'm going to use a 2 formula method just because I don't want people to get confused. You are more than welcome to use this setup right here to solve the whole thing. So what can I plug in, what can't I plug in here? So realize that in this formula right here, the new one, the boiling point elevation formula, you're given a constant, so you always have that number given to you, and it's right here, and it would be given to you. Kb for water, because it's our solvent, is 0.512 degrees Celsius per molal, and that is equal to the delta TB. In this case, the change in the temperature of the boiling point is 2 degrees. We can plug that in directly without any math at all. And the only unknown in this equation is molality. So again, you could do more if you want to combine the formulas, but if not, you can go this route as well. So in this case, to solve for molality, you divide both sides by 0.512. And by doing so, you're going to get M equals 3.91. And again, that's little m, little l. So now I can take that and plug it into my formula for molality. So again, I know that is molality, and that is equal to moles of solute. In this case, my solute is NaCl, so moles of NaCl up here. And in the bottom, I want kilograms of my solvent, which happens to be H2O. And again, I was given how much solvent I had, 1,000 grams, and if you remember, that's 1 kilogram, so that makes it easy. And I don't know how many moles of NaCl. So again, I'm set up with a 3-variable equation, and I have 2 of the knowns and 1 unknown. So solve for the unknown. You can cross multiply. It's pretty easy with 1 being there. So X, in this case, the number of moles, is 3.91. So we're really close. We almost know how much we need to put in there to make this boiling point increase by 2 degrees Celsius. The last step I need to do here is change moles to grams. Moles of NaCl to grams of NaCl. And 1 mole is equal to the molar mass of anything. So in this case, 3.91 times 58.5. And I get 228.7 grams of NaCl. That's quite a bit of salt. So if I want to make sure my water does not boil until 102 on the thermometer, if I had it in there, I would have to add 228 or 229 around grams of salt to exactly 1,000 grams or 1 kilogram of water. And the next question here, it's the same idea. However, we're looking at water or the solvent from a different angle. Instead of increasing the boiling point, we find that as you add more stuff, solute, the freezing point decreases. It takes, you have to take more energy out, if you will. Remember, we don't add cold, we take away heat to make it freeze. So in this expression, it's very similar. This is the change in the temperature of the freezing point. So let's change in the temperature of the freezing point. It's basically written here in words. And it is the freezing point depression, that is that thing right there, is the Kb. And molality, again, is M right there. So notice I have a new constant depending on your solvent again that we'll use to figure out how much lower that temperature will go, that change, based on the concentration. The higher the concentration, we see the more change. And this Kf allows these two to work together. So it says calculate the freezing point depression of a new and the new freezing point. So 2 things, the freezing point depression, which is delta Tf, and the new freezing point. So I need the freezing point. So 2 things, based on a solution that has 400 grams of benzene and 200 grams of acetone. This is a weird solution, and it doesn't say what is dissolved in what, but if you remember, this number is larger, so this is going to be the solvent, and this number is smaller, so this will be the solute. Again, looking at the 2 formulas I'm working with, I've got this, and I've got molality, which is moles of solute over kilograms of solvent. Now, I always have the Kf, so check, I have that. I don't have molality directly, but I can get it from the information I'm given, so I don't have that. And I don't have the change in temperature of the freezing point. So this equation is not where I want to start in this case if I'm using 2 different equations. So I'm going to start with this one. I should be given at least 2 of the 3 things to figure out the unknown. So in this case, like I said, I'm given 200 grams of the solute. In this case, it's acetone, so C3H6O. And remember, my solute, again, so solute has to be in moles based on my formula. So this is going to be converted to moles. So 1 mole equals the molar mass. For acetone, I believe the molar mass is 58. And 200 divided by 58 gives you 3.45 moles of acetone, which again is C3H6O. That's my solute, so it's going to go on the top of my molality formula. And then my solvent, again, is the larger number, 400 grams of benzene. And you probably can do this in your head, but again, I'll do it just for the heck of it. 1,000 grams equals 1 kilogram. So we're going to move the decimal point, and we get 0.4 kilograms of benzene, my solvent in this case. So I can get my molality from this right here. There's my moles of solute over my kilograms of solvent. 3.45 divided by 0.4 gives me 8.63, and that's molal. I can now plug this in. I've got 2 of my 3 variables to figure out the change in the temperature of the freezing point. In this case, notice we're working with benzene. I threw in a different solvent there, so we want to use this Kf because we're dealing with benzene. So in this case, the delta Tf is equal to Kf, so Kf times molality. Kf in this case is 5.12 degrees Celsius per molal times, again, molality in this case, we just figured out is 8.63, and this will equal the delta Tf, the change. So notice what happens here. You've got molality here and down here in that unit, leaving you with degrees Celsius. So 5.12 times 8.63 gives me around 44.1 Celsius. That is the change in the temperature of the freezing point, or the freezing point depression. That's this right here. So the freezing point depression is 44.1 degrees Celsius. The new freezing point would be in relation to what benzene typically freezes at, so it would be plus or minus. So off the top of my head, I do not remember what benzene freezes at, but let's say it were to freeze at 0, like water. In this case, I would write negative 44.1 Celsius, negative 44.1 Celsius. And that's it.